One, starting with the fundamental counting principle. So in this unit, we're going to solve problems involving application of the fundamental counting principle with permutations, that's restrictions and repetitions, and combinations, okay? Permutations, combinations. We also explore patterns in the expanded form of x plus y to the n, and solve problems using this binomial theorem. So the first thing we're going to look at here, just the introduction, and I tried to draw it last class, and I won't for this one because the tree diagram is a little bit tedious, but I think you guys get the idea of it. But Joe's shopping for a car. The dealer says he has 3 different models and 5 different colors for each model. Use the tree diagram to determine how many different choices Joe has. So in terms of tree diagram, which would we, how do we figure out how many choices? So model 1 can be these 5 colors. So it's a model 1 blue, model 1 red, model 2, model 3. Yeah, well, you will go 5 times 3, but simply from the tree diagram, you'd count the end branches, right? You count all these, which is the 15. Okay? And so there's 15 options for the car, which is correct. So let's look at the number of choices in the model and the number of choices of color. How do you see these numbers to arrive at the answer? Well, in answer A, when we count, we get 15. There's 3 models and there's 5 colors, and so we get the 15 options. That's kind of the beginning of the fundamental theorem of counting principle. Sorry, not theorem, fundamental counting principle. So it says consider a task made up of several stages, okay? So just in general. The number of choices for the first stage is A, the number of choices for the second stage is B, and so on through C, D, etc. You would simply times the choices to get the possibilities. Okay, so just keep that in mind. That's the fundamental counting principle. Any questions on that? Okay, so we're looking at the beginning one. So again, I'm not going to do the tree diagram just because it's actually really hard to do with this pen. If you want to sketch on yours and it's really neat, that's great. But part 1, part 2, and part 3 of a toy has different color options, okay? So part 1, there can be red, white, blue, or pink. Part 2, maybe orange, purple, or black. Part 3 can be just yellow or green. So how you'd start this, I'll just show you how you'd start it. You just start with the red for part 1. You would start with the white for part 1, the blue for part 1, and the pink, and then you'd branch off from there for 3, for 3, 3, for 3, and then you do 2 off of those. I'm not going to do it all, just like I said. The tree diagram, that's how you could draw it. If you do the fundamental counting principle, it's simply going to be the 4 times the 3 times the 2 for color options for each part. So you have 24. So when you do a tree diagram, you'll have 24 end branches all the way down. Okay. Maybe I'll just draw the red branch for you. So red can be the first part red, then it can be orange. Okay, it can be purple. It can be black. And then red-orange can be yellow or green. Red-purple can be yellow or green. And then red-blue can be yellow or green. And so just that one branch of the 4 is 1, 2, 3, 4, 5, 6 options. So if we have 4 of those branches, it's 4 times 6 for 24. Okay, so that's just a piece of the tree diagram. The tree diagram is more of an illustration so you can visually see how it's happening. It's not necessarily you need to know how to do a tree diagram. It's more so you can see the visual representation of what you're multiplying. Okay? Any questions on that? No? Okay, so in the previous example, the toy consisted of part 1, part 2, part 3. The total number of possible toys was found by multiplication. An example involving and, you're going to do multiplication. So and is part 1 and part 2 and part 3 to make the toy, right? So we can multiply those. We're going to talk about when that's not and in a little bit, but think about that for multiplying. So Math 30 quiz consists of 8 multiple choice questions. Each question has 4 choices. How many different sets of answers are possible? You'll probably get this wrong the first time. What is it? It is not 8 times 4. That's correct. Good job. Nope. Not 8, because we don't have 8 choices. Each question we have how many choices? 4 what? 4 to the power of 8. Because each question you have 4 options. So there's 4 options. So this is why. Okay? So this one is 4 times 4 times 4. I'll write all the way out just so you can see. 1, 2, 3, 4, 5, 6, 7, 8. Or it's 4 to the 8th. This is why. Question 1, I can answer A, B, C, or D. There's 4 options. Question 2, I can answer A, B, C, or D. There's 4 options. And so the different combinations of your test, like all the answers you pick, is a very big number. Okay? It's not just 32. It's not just 256. It's 4 to the 8th. So this is why, like another illustration, so if you want, I'll do it one more time if you're not visualizing it. If I just selected A for all my answers, that's possible, right? 1, 2, 3, 4, 5, 6, 7. That was good. Okay? And then I could go B, A. And I could do this for a long time, is my point. I can just switch the B to question 2 and switch to question. I mean, it just goes for a long time. And so how you do that is you calculate by 4 to the 8th. It gets all the possibilities. 4 to the 8th is 65,536 possible answer selections for 8 questions of multiple choice. Interesting. Right. Well, there's a little bit of probability in that because obviously you have a 25% chance, like each time. And then obviously multiple choice, hopefully you can narrow it down. But yeah. Yeah. All right. So now, when solving problems involving restrictions, it's important to understand the restrictions is dealt with first in the example below. So you have to take into account sometimes there's restrictions, which means you have a limited amount of possibilities of what you would expect. Okay, so let's look at this. Look what this says, and it's very wordy. So like, ask questions if you need any clarifications. Okay, so when Eric has been assigned the task of determining how many odd 4-digit numbers there are. So just 4-digit number like 1201, 1365. Odd an odd 4-digit number. Okay, not the numbers within, just that it's an odd number. Okay, so like it could be a 2 could be in there, but it'd be like 2003 would be an odd number, 4-digit. Okay, so it says he's been told such number as 5267 is a 4-digit number, whereas 0267 is classified as a 3-digit number. So what does that mean? We can't have what? We can't have 0 for the first digit. That's what the restriction's telling you. Okay, so 0 can't be in the first digit. Right, we're going to talk about that. Okay. The first step is shown his work. What he's doing, he's putting down the possibilities for each digit. That's what he's doing right now. So what does the 5 represent? Odd numbers. 1, 3, 5, 7, 9. There's 5 options that he can have the last number be. That's his first step. So he has 5 options he's limited to end with. That's a restriction, correct? Okay? Since it must be odd. Okay. The second step of his work is shown. Explain why he has the number 9 in front. Okay, did you hear that? We can have all numbers, all digits. How many digits are there? There's 0 to 9, which is 10 digits. But we can't use 0, so then we have 9 options. There's 9 options for the first digit because we can't be 0. Okay? If you're not seeing what I'm saying, there's 10 numbers here, 10 digits. The first one can't have that. It can have everything else, which is 9. That's why that's 9. And again, these numbers are possibilities. We're not coming up with the number. We're coming up with the possibilities of numbers. Okay? So that's what's here. So 9, because we can't start with 0. Okay? So what goes in the middle? 10 and 10. The middles are fine. We can use all digits for the middle. Multiply those 4 numbers, we will get the number of odd 4-digit numbers that doesn't start with 0. Okay? 4,500. $4,500. Any questions? On which one? Because we can use 0 now. So you hear that? The middle is higher than the outside because the middle can have zeros. This is going to be 2060 or 2605. Could be a number. So 2605, right? Okay, so 4500. Good? Any questions on that before we go to part B? That's good. You guys are listening a lot better, so that went a lot smoother, so thank you. All right, B. Eric has now been assigned the task of determining how many odd 4-digit numbers there are which have no repeating digits. So the same question, but we can't repeat numbers now. Okay, so this gets a little bit interesting. So what we're going to do is that we're going to say, okay, the first step is valid. The first step's okay because they still want odd numbers. So the first step of being a 5, like our 5 options, is still 5 here, right? Because we still have to end with an odd. But where do things start changing? Not 5 at the start. You guys hear that? She said exactly right. Now that we have put an odd number here, this used to be a 9, right? And these could match. They can't now. So by putting a number here, it eliminates an option here. So now we can only have 8 options here. Because you can't be 0 or the last number. You can't be 0 still or that last number because they can't repeat. So then now the next thing to think about, these used to be 10s. Okay, close. This one's an 8 again. That's the curveball because this can be 0. So the way I think about this is, this used to be 9, but it can't match that one, so now it's 8. This used to be 10. It can't be either of those two, so 10 minus 2 is 8, and this is 7. So it keeps declining.
But it can't be 8. And it is 8. So that's just the exception.
Right. These ones are confusing because this one can't be 0 or the end. This one can't be the front or the end, but it can be 0. So this one's okay with 0, so it gains 1 and comes back down. Okay. Questions? Okay, so I'll kind of write out a little bit. So the last digit's still odd. So 5. The first can't be 0. Or the last number. So that means it went from 10 minus 2, so it has 8 options. Used to have 10 options, can't be 0 or the number we picked, so now it's 8, so that's why the front's 8. Okay, the second number can't be the last or first number, but can be 0. So that makes it a 10 minus 2 for 8. And then the 7's just because it's 1 less. Okay, so then if we multiply that, you're going to get 2240. So essentially, it's just a little bit less than half. A little more than half. No, a little bit less. It'd be 250, right? Yeah, it'd be 2250. A little less than half. Okay. All right. Now we're going to do even like kind of a little interesting with like license plates here. So a car-numbered plates in African country consist of a letter other than I or O, followed by 3 digits of which the cannot be 0. The first can't be 0, sorry. Followed by any 2 letters that are not repeated. How many different car number plates can be produced? So the first one is that letter that can't be I or O. Then I have 3 digits, numbers. And then I have 2 letters that these ones just can't be repeated. The confusing part from last class was these 2 letters aren't considered repeated with this guy. Just these 2 can't be repeated. It can't be AA, it can't be CC. Okay? All right, so what number for possibilities goes to start? Huh? 24. 26 minus 2, because the I and O I can't be. Okay? What goes for the first number? 9, because it can't be 0. What goes for the second number? Doesn't say anything about repeating numbers. We can be 0 now, too. Okay? So it goes back to 10 because the numbers can be repeated, that's fine. And the second and third can be 0, so they actually have more possibilities than the first. So it's 9, 10, 10. Okay? And these last two letters, they don't have restrictions of I or O, so it's going to be what? 26, 25. Because I can't repeat those two. So I can pick T, I just pick anything but T. And it doesn't, this one's not related. These two can't be repeated. The wording's not good. But they're saying these two can't be repeated. It can't be AA, it can't be BB. But it can be okay if it's like, if this is R, I can go QR. That's okay. Just the last two letters can't be the same. That's probably what they should say. Last two numbers can't, or letters can't be the same. Okay? If you multiply this, you get a very healthy 14,040,000. 14,040,000 combinations for license plates. Yeah. Well, that'd be enough, right, for Calgary, or for Alberta, probably, for sure. Okay, let's do example 5. Now we're talking about the and a little, or the or a little bit, but okay. There are 2 routes from Pitland to Queensville, 3 routes from Queensville to St. Luke's, and 3 routes from Pitland to Rutherford, and 1 route from Rutherford to St. Luke's. Okay, how many routes are there from Pitland to St. Luke's that go through Queensville? Okay. Right, so you're going P to Q to S. How many routes go from P, Q to S? So how many routes from P to Q? 2. How many routes from Q to S? So there is 6. There's 2 routes from Pitland to Queensville, sorry. And then 3 routes from Queensville to St. Luke's. So it's 2 times 3 for options. So 6 paths you could make. Okay, how many routes are there from Pitland to St. Luke's past through Rutherford? So you're going the other way. So you're going here, here. There's 3 to Rutherford. And then from Rutherford to St. Luke's, there's 1. So that's P, R to S. So then how many total routes are there from Pitland to St. Luke's from that diagram? Good. 9. Yep, you add these because there's 6 going to Queensland first, and there's 3 going from Rutherford. Very good. You guys got that a lot better in last class. Any other questions with that one? Okay. So this is an example of the OR. Okay. So it says in part C, we could travel from PS via Q or PS via R. The total number of routes is found by adding the answer in A to answer B. In this example, it's involving the OR because I'm going to St. Luke's through Queensville or Rutherford. So by using the word OR, you would add those totals. Does that make sense? So you would add those totals. Right. And is multiplying, or is adding. Okay. All right. Here we go. So what we have is what it says, telephone numbers allocated to subscribers in a rural area consists of one of the following. The first number, so these are 2 different types of phone numbers. One is the digits 345, so the first one's the 345 is locked in, those don't change, followed by any 3 digits. And further just means 3 digits, not bigger than 5. Okay, so that was confusing for last class. So just 3 digits. Okay, that's the first option. Or the second option, the digit 2 followed by one of the digits 1 through 5, followed by any 3 further digits. Yes, this one's shorter. No, it just means anything. Like, it means the next, it's talking about further digit. It means like the digit place. So like, they're saying 3, 4, 5, and then the further digits, like farther, are any digit. Yeah, so the 5, the more than 2, that doesn't matter, okay? Okay, so this one here, if it's 3, 4, 5, and then any 3 digits, what would that be? 10, 10, 10. Now, keep in mind, we're not multiplying that, right? Those are locked in. Those aren't options. So this one's simply 1,000. There's 1,000 options. 10 times 10 times 10. Yeah. And so this one would go to 5, because 1 through 5 is the next digit option, and then 10, 10, 10. Again, the 2 doesn't count. That's just locked in. So it's 5,000. And then we're going to add those two because we can use or. They said either work, so 6,000 options, if it could be one of those two. Okay, last page. Any other questions? Okay? It's not that bad. This next part gets pretty confusing, though, so it's okay. I like the positive attitude. All right. Consider the class example 3, which Eric was asked to determine how many odd 4 digits there are. Now we're going to do an extension of that. So the one we talked about with odds, we're going to talk about evens. So how many even 4-digit numbers there are, and how many even 4-digit numbers have no repeated digits. Okay? So part 1's fairly straightforward and easy, but part 2 is going to take a little bit of work. Okay? So let's look at part 1. Determine the answer to part 1. How many even 4-digit numbers are there? So we're doing the same thing that he did for the previous. Okay, so even numbers. How many digits would represent an even number? 5 still, because you do count 0, because stuff that ends in 0 is even. Now, 0 is not even number in math, but stuff that ends in 0 is. Okay, so we still have a 5 here. Good. Okay, now what do we do? This can't be a 0, so we put a 9 again, so it's the same. So straight even versus straight odd is actually the same for this one. It's 4,500. Okay? Now you're going to see where the frustrating part comes from. Wait, so it's 5 because... There's 5, 0, 2, 4, 6, 8. 5 evens. Who wants to take a stab at why B is going to be really confusing? Because you can't what? Kind of. So the problem is that we're going to have to actually break this into 2 options, because this is why. There's 5 options here, right? This can be 0 anything, okay? But if it's not going to repeat, there's a problem here because, let's see if you can see it. Which number's a problem? So, okay, check this out. If I put a 0 here, you know I can't repeat, right? Does that affect the number we've been putting there? No, because we already took 0 out of this one. But if I put a 2 here, does that affect this one? Yeah, it can't be 0 or 2 now. And so that overlap of the 0 is making things complicated that we can't write it in one multiplication. We have to break it into 2. Okay? So let me explain that one more time. See, some light bulbs come on, some not quite on yet. So if you put a 0 here, that will not affect this guy at all because he couldn't be 0 anyways. So he could be 9 still. If you put a 2 here, it can't be 0 or 2 now, and now it's an 8. And so you have to think of the 2 situations. So we have to treat this guy separately. Yes?
Okay, so then why isn't the 5 included for the first number? Then why is it not allowed to have 5 or 0?
So say that one more time.
So like you're saying that if you put a 2 in,
Mm-hmm.
then now the first number, it can't be 0 or 2, so
Mhm.
it's 8. So y in the beginning, like y is 5 allowed, but then
So remember, 5's not allowed. 5's the possibility number, Maddie. So 5 is the number of even numbers it could be. That's what this 5 represents, the possible numbers. That's the number of possibilities. It's not 5 is not in here because that's odd anyways, right?
yeah.
So this stands for 5 even numbers. That's what that stands for. So we're writing out the possibility line. It's almost think about it, not an actual number. A lot of people thought that too. They're like, why is it a 5? We thought it has to be even. You're right. It's 5 even numbers. So let's look at this here. So let me show you. So we just explained. I'm going to write it here. So the last digit is 0. Spot 1, I'll call this spot 1 right here, is unchanged. If last digit's bigger than 0, bigger 0, so like 2, 4, 6, etc., then the first spot is 1 less. So essentially we have to think about the patterns separately in like an or, okay? This or that. So what we're going to do is let's do the 0 one first. So if I'm saying that this ends in a 0, what's the possibilities for the last digit? Like how many possibilities is that? I'm forcing you to pick a number. You have 1, right? I'm saying 0, so you have 1 choice, right? You can't, there's not choices. Does that make sense? When you don't have a choice, it's 1, which is cool because that also means that's why it doesn't multiply. It's a 1. Right, and then so the first one, so if this is a 0, okay, this is the, I'll say this is the 0 ending piece. That means this is a 9. That's a 9, because if it ends in 0, we already couldn't be 0. So it's going to be 1 through 9. So the ends a 1, because I'm making you pick 0. You have 1 choice, a 0.
Oh, choice, right, okay.
You have 1 choice. Remember, these aren't numbers, these are the choices. You have 9 choices for the front now. How many do you have here? So if this is 0, this is 2, that means you're at 8, because 2 have been canceled out. 2 things you can pick have been canceled out. And then you have a 7. Okay, questions on that? So that's your first piece. And the other one is when it doesn't end in 0. Or, so, if it's even numbers except for ending in 0. So how many do we have? 4. There's 4 even numbers besides 0 for ending, so we put a 4 there. Now, that does change the front now, right? The front can't be 0 or what this is. So you're down to 8. You're down to 8. Now let's see if you can get the next one. The second one, what? The second equation represents 0, this represents 2, 4, 6, 8. We're doing those separately because of the 0. What are the possibilities for the second piece?
I feel like that's a stupid answer.
So,
I've been wrong every
here's the thing. Of these 4, did we say that possibility is 0? Nope, 0 couldn't be here. Could 0 be here? Nope, can 0 be here? So it's 8 again. It's not these 2 plus 0.
I just knew that was coming.
So the second one can be 0. So the second one's the first time we're saying it can be 0. We can write it out. Okay, here, watch. Maybe I'll show you this way. 4. This 1 represents 0. This 4 represents 2, 4, 6, 8 are the possible numbers that can go here. This represents 0, sorry, it can't be 0. 1 through 9, but not what spot 4 is. I'll just put SP4. It could be a 1 through 9, but not this guy. So that means instead of 9, it's 8. This one can be 0 through 9, but not spot 1 or spot 4. So there's two things we're subtracting from 0 to 9 is how many? 10. So it's 10 minus 2 again, so I get 8. That's where the 8 comes back. This spot right here, by what we're doing, is the only one so far that can have 0. That's why it gained 1, and then this is 7. Yeah, like I said, it's a little complicated for sure. So the first piece, so these are ors. So we multiply the top 98 times 7. You get 504. So 504 options for the top, plus the 1792 for the bottom. So your total without repeating even digits is 2296. 2296. So again, what that means is 2,296 combinations of 4 numbers that can be even without repeating digits and no 0 in the front. All right. And definitely, Maddie, try to explain more too. Okay, so I'll come back there. It's fine. Okay, consider the number of distinguishable 4-level arrangements. Slow down. Distinguishable means like different. Okay, so not repeated. Okay, and the word English. Note there's an implication that each of the letters in this word English only occurs once and cannot be repeated. That's what I just told you. Okay, so here's what we're going to do. Determine the number of distinguishable four-letter arrangements can be formed from the word English if any letter can be in any position. So what that means is picture these, when they say stuff like this, picture the word English letters in a bag, and you're grabbing them out one at a time. So there's 1, 2, 3, 4, 5, 6, 7 letters. So my first grab, there's 7 possibilities. My second letter grab, there is 6. My third's 5. My fourth letter's 4. So I'm keeping the letters. That's what I mean by distinguishable. You're not putting them back in. Okay? So then for A, that possible combination is 840 different ways you can get something to come out of there. L, I, S, H, I don't know. Anything like that. So how does it change if I say the first letter must be an E, though? So then it goes exactly. The E is locked in, and that we just picture that as a 1. Good. And then it's 6, 5, 4. So 120 for that way. Interesting how just one less letter, right, makes it much smaller. A little tricky one. The first and the last letters must be vowels. How many vowels are there? There's 2. So the first letter must be a vowel, so what do we put there? How many options are there? 2. And then in here it's, good, 5. Is it 4? Yeah, we're doing 4, right? And 1, yep. So the outside's the vowels. There's 2 vowels, and then at the end you have to pick there's only 1 vowel left. 6, because we took 1 out of 7. So we have 6 left, 5 left, and then the last one of the vowels. We're not allowing them to repeat. Like when you take that out, you keep it. That's what I mean by distinguishable. We won't repeat vowels. Yeah. And we're going to talk about the difference in that later, Sadie. This one's 12. This is 60. There's only 60 ways you can do that. Or no, 40. Can't multiply. Hold on. What did we do wrong here? So if we took, so here we go. It's not 6 and 5. Got ahead of myself. Because if we have 2 out, yeah, it's 5 and 4. Because you can't grab that vowel. The vowels have to be on the end. Sorry about that. What's that? Yeah, now it's 40. So the reason it's 5 is because there's 2 vowels that are we're only going to grab in the front and the back. So there's 5 ones that aren't vowels, and there's 4 ones that aren't vowels. I forget one of them. So think in terms of non-vowels and vowels. The word must contain a G. So whatever you grab out, you must have a G in it. So that would be G, 6, 5, 4, or 6G, 5, 4, 6, 5. I'm writing all the combinations. You don't have to do this. I'm just trying to show you the illustration. Like everywhere you get a G, right? So you get a G in the first, the second, the third, or the fourth draw, right? And then it'd be 654 times either way. So that's 120 for each of them. So times that by 4, 480 possible G words. Okay, and that's it. And we'll stop there.